Let's go through activity 6. So I'll change this to solutions. And the one thing about activity 6 is that after you load up library reg class, you want to make sure to define the VIF function, because I accidentally left that out of reg class when I made it. So I'm highlighting lines 13 to 43, and I'm running this so that the VIF function does get defined. All right, so for this activity, what we're doing is we're looking at the launch data set. So if I load this up, I look and I see that there's 420 different variables. So this is a very large data set. And if I do question mark launch, I can read about what the purpose of this data set was. Basically, it's containing the profit of newly released products over the first few months of their release. And we have a column called profit, which we want to predict, and 419 predictor variables. This is real data. It's from the Kaggle competition, and so these variables are anonymized, so no trade secrets get divulged here. So we'll just have to treat them as just x1, x2, etc. So this is a lot of data, and to make our problem a little easier, what we're going to do is we're going to restrict ourselves to predicting profit from just the first 10 predictor variables in the data set. So here what this command is doing is it is taking the original data set, launch, and then just extracting the first 11 columns. So the first column corresponds to profit, and the remaining correspond to the first 10 predictor variables. And it's storing that result in a new data frame called PL. So PL is the data frame that I'm going to work with for the rest of the activity. Let's try to predict the profit of this newly released product based on the values of these 10 predictor variables. So a good place to start is to visualize the relationships between all of the pairs of variables in the data set. So to make a scatterplot matrix of all pairwise relationships, pairs is the command I want to use. And in general, the syntax is just y_twiddle, and then spelling out the names of all of the x variables that you actually want to be looking at. So in this case, the name of my y variable is profit. And I could type out x1 plus x2 plus x3 all the way up to x10. That's a bit tedious, so instead I'm going to use the twiddle dot shortcut. If I do profit twiddle dot, what that's going to do is it's going to just automatically include all of the other columns in the data frame. So when I say data equals PL, what this will do is it'll make a scatterplot matrix with every variable in the data frame. Let me make the plotting window a little bit bigger. And also, we're going to go ahead and add in the additional arguments PCH equals 20 and CEX equals 0.3 to make those points small. So we're going to have a lot of different plots, and the first thing that we do is we look to see, all right, are there any variables that are strongly correlated with our y variable profit? The top row of plots shows you the scatter plots where the y variable is the vertical axis, as we're accustomed to, and the predictor variable is the horizontal axis. So we scan across here, and our first task is to name one of the predictors that looks to have a strong relationship with profit. So basically looking for a stream of points with not all that much scatter. And, well, x2 and x4 look like they're reasonably strongly correlated. So either one of those. So x2 or x4 is a good answer for this. They look to have the strongest correlations, at least, of the other variables. It's the stream of points with the least amount of scatter. So I kind of look to see, well, what variables seem to be related to profit? Do I have at least approximately a linear relationship going on between my predictor variables and profit? And this looks all right here. Maybe there's a hint of curvature, maybe some other curvature. It's hard for me to tell, but no very painful, obvious nonlinearities present in the relationships between y and x. So the remainder of the plots here, and we're just going to focus on the plots in the upper right. The plots on the lower left are just mirror images of the ones up here. These remaining scatter plots show you the relationships between the predictor variables themselves. And the correlation between the predictors becomes important when you try to estimate the values of the coefficients in the model. The more correlated your predictors are, the harder the time the model has in estimating those coefficients. The standard errors become a bit large. So name one of the predictors that looks to have a weak, non-existent relationship with profit. So I guess we're still back up here. Well, x1, I don't see any sort of linear trajectory whatsoever, just kind of a flat horizontal band of points. So I'm going to say x1 sure doesn't. And it's hard for me to really tell if there's anything else going on, but it looks like, the range of possible y values gets smaller for larger values of x here, here, and here. So really x1 is the only decent response for this one. C asks, looks like, or says, name one of the predictors that looks like it may have a nonlinear relationship with profit. So I guess I'm still back to that top row. I don't know, maybe x2, maybe there's a hint of nonlinearity. Maybe x4, it's hard for me to tell. It's hard for me to tell really what's going on here. But maybe x2, maybe x4. Name two predictors that have fairly strong association with each other. So what scatter plot in this lower right-hand part seems to have very little scatter? Well, there doesn't look to be any super strong relationships going on. But this one kind of catches my eye maybe. Is there anything else that's sort of elliptical? Yeah, there's really not all that much going on here. So nothing is strongly associated with each other. But maybe, well, we did decide x2 and x3, that looks like a linear trajectory. So x2 and x3, or you see this weird kind of band of points right there. So maybe x5, x7. So, all right, we get a graphical assessment of the relationships of our predictor variables with y, the very top row, and an idea for how correlated the different predictors are with the rest of the scatter plots there. All right, so let's go ahead and fit the regression model. And our syntax for fitting the model is what we're used to. We're going to give the model a name, by default m here, left arrow, and then lm. And the syntax for linear regression, simple linear regression, was y twiddle x. And same sort of thing here. Actually, I can do the exact same syntax for the pairs. So here's my shortcut here. I could say profit twiddle x1 plus x2 plus x3 plus x4, etc. But since I'm going to be predicting profit from all of the variables in my data frame, twiddle dot is shorthand for saying, hey, predict your y variable from all of the columns available. And that's from the PL data frame. So that will fit the model. And then we want to check to make sure the assumptions behind this model look reasonable. So check regression M. And let's look at the diagnostic plots and also the tests. So we first look at the tests to see if we passed everything. We hardly ever do, and we see a lot of failures, a lot of p-values less than 5%. So we fail the test for equal spread. We fail the test for normality. The test for linearity of the overall model is not available. There weren't enough duplicate rows with identical values of x's. So we'll have to check that with the residuals plot. And we do fail the test for linearity for the residuals versus a few of the predictors, all these p-values less than 5%. So, all right, we have our work cut out for us. We have to check to make sure these aren't deal-breaking violations. Part A makes a comment about these kind of odd diagonal lines that are visible in the residuals plot. So when we look at the residuals plot, we don't want to see any sort of pattern. Our model is supposed to explain all of the variation in y and how it's related to the x variables. If we see a pattern, that means our model is incomplete somehow, and that's a bad thing. Our model is not really accurately reflecting reality, and it needs to be tweaked. Here we do see that pattern, these weird odd diagonal bands. This actually represents a quirky property about the data set in that there was a minimum value of y that was hard-coded into the data. There was a minimum profit amount. All the products that had profits less than that were thrown out. And so these bands here actually just reflect the fact that there's a minimum profit in the data set that we're not allowed to have values less than that. That turns out to manifest itself by this pattern here, but there's nothing we can do about it. So otherwise, this residuals plot looks all right. I don't see any sort of global curvature, and I see that the typical size of the residual is about the same, positive and negative everywhere. So I'm happy with this residuals plot except for these odd diagonal bands. It's just that pattern we're going to have to live with. We know our model's wrong to begin with, and it looks like there's something in the relationship we won't be able to capture with our model, but there's nothing we can really do about that. So part B says the p-value for the linearity of the overall model is not available because no two predictors have the exact same set of x's. Does the linearity assumption of the model look reasonable? Well, yeah, we didn't see any sort of curvature. Yes, no curvature apparent in the residuals plot. We know the equal spread test has failed, but does it look like the violation is severe? Well, no. The typical size of the residual looks to be the same everywhere. the typical size of the error the regression makes is about the same regardless of the predicted value of profit. And that's what we want. We don't want some individuals having smaller errors typically than others, depending on what profit they're predicted to have. We want to have the same typical error everywhere. Part D, the normality test has failed. Does this appear to be a problem? Well, we'll look at the QQ plot. I'll zoom in on that plot a little bit. And this looks great because we do see a point or two outside of the upper and lower dotted bands, but that's happening at the very edge of the QQ plot, and that's to be expected. So this looks fine. And so no, this is not a problem. The points are more or less inside the upper, lower dotted bands. So there's small departures outside at the edges, but this is to be expected. Okay, so in addition, when we check the assumption of a multiple regression model, we also need to make sure that there's no leftover pattern in the residuals versus the x values themselves. If there is, there's something missing in the model, some extra complexity to the relationship between y and x that's not being captured. So we can get those plots by rerunning check.regression and by adding the argument extra equals true. So that'll spit out the exact same test. It spits out the standard 3 diagnostic plots, and then it says press enter to continue to the residual versus predictor plots. So I press enter, and here is the plot of the residuals versus the x1 values, residuals versus x2 values, etc. So what we need to do is we need to go back and check to see, are there any patterns of the residuals with x2, x4, x5, x7, x8, and x9, and x10, all the ones that failed. And I'm just going to scan through them all. I don't see any sort of problems here, any sort of curvature. x4 through x6, I don't see any obvious curvature going on, no bend in the residuals plot, so we're fine. No bends here, and no bends here. So you know what? Whatever violations that must have been occurring must be small enough for me to ignore. So I will say that no, there are no obvious nonlinearities in these plots. So in other words, we're coming to the conclusion that the regression model does look to be a reasonable model, a reasonable reflection of reality, except for that hard-coded lower limit of y. So let's go ahead and use it. Let's get a summary of the regression model. So summary M, I'm going to actually go ahead and include that little bit of our code. I don't know why I didn't include that in the original write-up. So summary M. And we need to ask ourselves, okay, is the model statistically significant? Is it predicting the profit better than the naive model, where we just assume each individual's value of y is best predicted by the overall average? So we look at the number in the very bottom right, the p-value here, and that's telling me the p-value for the test of significance of the model as a whole. It's less than 5%, so yes, the p-value is less than 5%. And so what that tells me is that, yeah, the model is predicting the profit better than the naive model. So basically, if we filled up a regression model with completely random, unrelated predictors, then our model is predicting significantly better than that model, better than no model at all. So our model is predicting profits better than the naive model, or a model full of predictors completely unrelated to profit. All right, so what variables are statistically significant? Well, we can look to see if x1 is statistically significant by looking at its p-value off to the far right. And the predictor is significant when its p-value is less than 5%. So scanning down, we see that most of them are. We see that x1, x2, x3, x4, and x5 are. x6 is not because its p-value is bigger than 5%. x7 is not. x8 is, though. So x8, which ones aren't? Well, just the opposite. x6, x7, x9, and x10. All right, what's the value of r squared? Remember, r squared tells you the percentage reduction in the sum of squared errors when you use your regression to predict the profit instead of the naive model. And r refers to that as the multiple r squared. So r squared equals to 0.7015. And we've learned that R-squared really isn't a fair assessment of how well the model fits the data, because a model with more predictors is always going to have a higher R-squared, even when those predictors have no information about Y whatsoever. R-squared always gets bigger when you add more predictors into it. So R-squared adjusted is a fairer assessment of how the model fits the data. It's basically the value of R-squared with a penalty term for how many predictors are in the model. So in order for the R-squared adjusted to get larger, any additional predictors really do need to be contributing additional information about Y. And R refers to that as the adjusted R-squared, and we see that that's 0.6968. So pretty close to the value of R-squared. This is a slightly fairer assessment. What's the typical size of the residual? Well, that's just asking me what's the root mean squared error. That's the residual standard error according to R. So the typical size of the residual is 0.2831. So typically values are off, the observed values are off from the what the model predicts by about 0.28 or so. Okay, so the coefficients of our regression model are listed in the estimate column. So we have 10 different coefficients for the different predictor variables. And we know they're just our best guesses of what the betas are, the coefficients of the population regression, if we had data on every single possible product in existence. So we know our estimates are wrong. They're different from the truth. How far off from the truth are they? Well, they're off by about a standard error or two. We can make a 95% confidence interval by taking our best guess and moving plus or minus 2 standard errors. So we can actually have R do that for us automatically by using the command confint on our model. And that'll spit out all of the 95% confidence intervals for each coefficient in that regression. So the 95% confidence interval for x1 we see is between these two very small numbers, 5.9 times 10 to the minus 8 up to 1 times 10 to the minus 7 here. Okay, so one thing that we've talked about is that the accuracy of your estimated coefficients, in other words, the size of the standard error, is actually tied in to how correlated the predictors are. When predictors are correlated, they in some sense have redundant information about Y contained in them. And when there's redundant information, the model has difficulty kind of determining what variability in Y can be attributed to x1, what variability in Y can be attributed to x2. It's hard for it to split up that variability, and so the resulting standard errors are a bit bigger. So with a bunch of redundant information, there's less information than there would have been had each predictor been independent. So these standard errors are larger than they would have been had x1 through x10 had completely independent sets of information. So we can look to see how much of an effect the correlation among predictors has on our estimates of the coefficients by running VIF. And the minimum possible value of the VIF is 1, indicating that that predictor is not correlated whatsoever with the other predictors in the data set. And values larger than 1 mean that that predictor is increasingly correlated with the other predictors. And the cutoff for a large VIF is related to the R-squared of the regression model. So going back, the multiple R-squared, the R-squared value here is 0.7015. So we would say we have a large VIF for a coefficient if the VIF was 3.5 or bigger. When we're above the cutoff, in some sense, the other predictors are doing a better job at predicting X instead of at predicting Y. And that's really not a good sign of predictors here. So, okay, there is some correlation among the predictors. We didn't see too much in the scatter plot matrix. So is it a problem? Is it enough to degrade our standard errors, increase their values relative to the case when all the predictors were independent? Well, no, not in this case. We're actually fine. The VIFs are all smaller than that threshold. So no, the VIFs are all smaller than 1 divided by 1 minus R squared, which was that 0.715, which equals to 3.5. So the standard errors are about the same size compared to the case where they were all independent. So upshot is we're estimating these coefficients with about as much accuracy as we could hope for, and so all our confidence intervals are pretty much the skinniest that they could be here. Okay, so we found earlier that x6, x7, x9, and x10 were not significant in the regression we might like to know, can we drop all of them from the model? So we know that when a particular predictor is not statistically significant, like x10 here, we can drop it from the model because it doesn't add any additional information about y above and beyond what the other predictors already add to it. But we can't just systematically drop all of the predictors that have p-values of 5% or bigger because p-values are model dependent. So if we were to kick out x10, the p-values for the rest of the predictors would change, and it might be the case that x7, x6, and x9 would have p-values less than 5% in that case. So what we do is we perform the partial f-test. We fit the model with all the predictors in it, and then we fit a simpler model that contains the predictors without the subset that we're interested in dropping. So basically x1 plus x2 plus x3 plus x4 plus x5 plus x8 from the PL data frame. So we have our simpler model, the ones without those non-significant predictors, and we have our complex model with all of the predictors in it. So one thing we know is that the complex model is going to fit the data better than the simpler model. It has more wiggle room to match up with the data points. And if we run the ANOVA command here, m.simple, m.complex, we see that by adding in these 4 predictors, the sum of squared errors gets reduced by 0.9. So is that big? Could that have happened by chance? We look at the p-value here. The p-value is less than 5%, so we say that the reduction in the sum of squared errors when these 4 predictors are added to the model is actually statistically significant. So it's unlikely to get a reduction in sum of squared errors that big if we were to add 4 random unrelated predictors to the model. So it looks like there is something in those predictors, we're not sure what, that actually does contribute additional information about predicting y. So we cannot drop these 4 predictors from the model since the p-value of the partial f-test is 0.02326, less than 5%. So something in those 4 predictors, when added to the model, basically allows us to predict y better than adding 4 unrelated predictors. So it is statistically significant, that reduction in sum of squared errors, so we don't want to drop those 4 predictors from the model. We could drop any one of them if we wanted, but not all 4 at once. All right, the last bit wants us to make predictions. And making predictions in multiple regression is a bit of work because we have to create a new data frame that contains the values for each x variable in our regression. So in this case, we're going to make a prediction for the profit of the product when the predictor variables are assuming very particular values. We're going to make one prediction for when each x variable is equal to its median, and another prediction when each x variable is equal to its overall average in the data. So we can get the median, we can get the average by running summary on our data frame. That'll report the summaries for every single variable in the data frame here. So we see we have median and mean values for x1, x2, x3, x4, etc. So I want to make one prediction when an individual's x1 value is this number right here. Their x2 value is 7,300, x3 is 6,300. Each value of x is equal to its overall median. And another when each value is equal to its overall mean here. All right, so the way that I do this, I'm going to remove this eval equals false so it actually gets included in the write-up, is to make the data frame and name it to.predict. So since there are so many values I have to put in here, what I'm going to do is actually split up this on numerous lines. So I'm going to do to.predict, left arrow data.frame, then a left-hand parenthesis. And then on each following line, I'm going to give the name of the column, which needs to correspond exactly to the name of my predictor in the regression. And they're just named x1, x2, x3, etc. So the name equals, and then the list of values separated by commas for the 2 predictions that I want to make, surrounded by parentheses and that c, so that we're treating these 2 numbers as a vector. So we want the first prediction to occur at the median value of x1, and the second one to occur at the mean value of x1. The first prediction to occur at the median value of x2, the second one to be at the mean value of x2, etc., etc. So most of this work's already been done. We just need to fill in what the median value of x9 was. I can just copy and paste this. And what both values for x10 were. And I see that the median value was 11. The first number in that sequence is the median value. The second number is the average. Okay, so let's run that whole command. You'll notice there's that right parenthesis that closes off the left parenthesis there. There's our to predict data frame. Those are the combinations of x values that we're making our predicted profits at. And now we have to just run the predict syntax. So I'm going to remove eval equals false so the results are actually inside the write-up. And the way I make my prediction, I say, well, what's the name of the model I'm making predictions from? Just M. Then I say new data equals, and then I give it the name of the data frame that contains information on the x variables at which I'm making my predictions. So I called it to.predict. And then I say interval equals confidence for a 95% confidence interval for the overall average profit among all products with that particular combination of x's. And if I do the same but just change confidence to prediction, I can get a 95% prediction interval for an individual product's profit. So I'll run both of these guys here. And so I can say that I'm 95% confident that the overall average product among all products whose combination of x's happen to be the median values of x in the data set is somewhere between 4.2 and 4.26. And for a particular product whose x values happen to be equal to the median values of x in each data set here, I find that there's a 95% chance that individual's profit is going to be between 3.68 and 4.79 here. So the prediction interval, as always, is much wider than the confidence interval. It's much easier to nail down a prediction for an average value than it is for an individual's value. And that's because individuals deviate from the average by random amounts. So there we go. There's your activity 6, and hopefully that'll be useful when working through the homework. The homework deals a lot more with interpretation instead of just getting R to run. So be sure to review the slides and come up with super precise statements about how you interpret coefficients and how you interpret the statistical significance. So this looks like it compiled pretty well, so I'll go ahead and post that, and good luck with the homework.